Good morning, everybody. Good morning. I seem to have made it a tradition that the first talk of the autumn season, wherever I go each year, I get sick. So I've come down with a cold, so you're sort of spinning for me a little bit at the moment. So please excuse my fragile state of health. Thanks so much to Stein for inviting me. So, as he mentioned, I founded the company CF Engine, but I left that company a couple of years ago, and I ended up writing a book called In Search of Certainty, which I'll show you a picture of later, which would turn out to be a sort of a life-changing event for me because a lot of people picked up on some of the ideas in this book. And the book tries to describe the work that I've done really over the past 20 years to understand systems. And as my background is as a physicist, I try to understand systems by looking at them and asking, how do they behave? Not what do we think they do, but how do they behave? By actually looking. And that was just sort of an unusual thing, and the journey was interesting. But after I left CF Engine, people started to pick up and invite me to come in and work with them at their different companies, from quite big companies like Apple and Cisco and IBM and Huawei and so on, to quite small startups, looking at ways to address the challenges of IT in what's probably been the most rapid expansion of scale and speed that's ever happened in the history of any kind of technology. So I spent the last couple of years traveling around the world giving advice on different things. And I started a project which I posted. I wanted to write some notes because as we were discussing how to make systems scalable, robust, resilient, I started to make some notes and thought, we need to formalize some of this information to be able to build the next generation of computer systems. Because if you ask computer scientists how do systems work, they say, well, they do what we tell them. We write a program, the computers execute the program, and so on. But of course, anyone who's ever used a computer system knows that that is a complete fantasy. The computer, on a good day, does something like maybe what we tell it to do, and a whole bunch of other stuff that we didn't tell it to do. So we really need to have a better understanding of this. And so I started this project, writing it down. It's already like 100 pages of documentation, and it's nowhere near finished. So this is a big kind of effort. Actually, speaking of Patrick Dubois, when I posted a tweet about this talk some time ago and said, how can we know when a system is working well? He tweeted back, because the users are happy. And I want to convince you today that actually that's not really a good answer. The users being happy could happen for all kinds of reasons, but unless they have some clear expectations as to what they can expect, and they match with the expectations of the people who've designed the system, then it doesn't really make sense to answer that, to make that point. Okay, so I'm going to try to answer this question with a whole bunch of other questions and see if we can think about it in a slightly deeper way. So the title has 5 keywords. How can we know when a system is working well? And I underlined the key names here, the key words. And I think these are the key words because when we ask who are we, it's important to say who are we making the decision about whether a system is working well. It's important because it's a subjective judgment. If I go to a restaurant and I order a meal, I order an identical meal to my neighbor, my fellow restaurant visitor, and I can be satisfied with the meal and they can be unsatisfied with the meal, even though it's exactly the same meal. We can disagree whether or not the kitchen kept its promise to deliver the perfect steak. So it's a very important subjective evaluation as to whether a system is working well from a particular perspective of every single user. What does it mean to know something? This is actually an interesting philosophical question that I spent almost 10 years working on, which ended up in the realms of AI, artificial intelligence, cognitive computing, which is burgeoning today. And I would like to argue that it's when we know a system in the way that we use the term to know a friend. So we know a friend because we've interacted with a friend for a long time. We've learned his or her characteristics, their foibles, their habits. We know when they're likely to cooperate or not cooperate. And so we are able to interact with them effectively. And in the same way, we can know a system only by using it and repeatedly using it and learning its foibles. What do we mean by the system? Well, that's where does it start and where does it end? A system, is it just this computer? Is it the computer connected to the internet? Is it this computer connected through the internet to the servers in the background? Is it all the other servers impinging on the traffic? So who is affecting my experience of the system? Where do we draw the boundaries? And then is it working? What do we mean by is it working? Is it doing what it promises to do? And who gets to judge that? And well, so good, bad, ugly, well, terrible. These are qualitative judgments that everybody makes from, again, subjective perspectives. So I think we need to think a little bit about what we mean by this question, how can we know when a system is working well? So, system. The way I design it, the way I describe a system is, because I'm a physicist, I think that there are a bunch of freedoms, a bunch of things we can change. These are the variables, these are the resources we can use, the things that we can change. We have certain freedoms to act. And then there are constraints which box us into a particular certain limits. Perhaps we can't exceed a certain speed, a certain storage capacity, whatever these limits are. So a system is always the balance between freedom to act, constraints on, or certain limits on the resources, but also limits on behavior. What a computer program is, of course, is a sequence of instructions or destructions that is executed in order to constrain the behavior of the computer to do a particular task. It can do all kinds of different things, but we constrain it to just one path through a particular space of possibilities. So it's really a bunch of freedoms and constraints. We can also think of it as a bunch of components, because it's natural to draw boundaries around pieces of the system and not just think of the whole system as a single entity. We manufacture systems in this way. We make individual pieces and connect them together. And we imagine systems in this way because it's too much work. It's too hard to conceive of the entire system in one go. So we tend to break things up into small pieces. The latest version of this, of course, you probably know, microservices is now, people now talking about microservices. How many people have you heard about microservices? Yeah, exactly. But this is really just the latest expression of what we would call modularity in IT, which is a very old idea. And the idea of modularity is that in computer science, is that we can separate out a particular problem and solve just this one problem in a generic way, and then we commoditize the result of this solution to make components that we can buy off the shelf, and then we can assemble components off the shelf into bigger devices. So we have our resistors, transistors, and capacitors and things in this thing, in the computer, and then we make it into a computer, and we make it into a radio, and we make it into a whole bunch of different systems. So modularization seems like a great idea. But of course, we can take that too far, because if we imagine that this small component always behaves in exactly the same way in all systems, and that it's enough to just ensure that all of these components are individually working, we lose the perspective that when we put them together in strange ways, they may not behave in exactly the way that we plan them to. they may not even be kept within their tolerances and their boundaries. And that means that the system, once we put it together, may exhibit behaviors that we never planned for, that we never designed, because we never really considered the whole thing as an entity. And this makes systems complicated. This is a question of scale. Scale and perspective, again, because individual users make their own judgments, and as we scale things up and put more and more of these things together, it becomes harder and harder to predict exactly what's going to happen. And so the notion of causality, causation, cause and effect, becomes entangled. And we cannot simply say that we designed this microservice to do this and this microservice to do that, and therefore the system will do exactly as we expect. It doesn't work like that anymore. Once we connect networks of components together in complex ways, the system can have behaviors that we never planned for or imagined. So things to understand, I think, about systems are, what was it that we intended the system to do? Okay, a system begins with our intent. We design it for a particular purpose. What does it actually do? Okay, so there's the intended behavior and then there's the actual behavior. These are two quite different things we need to understand. And too seldom do we actually make that distinction, and this is why I'm giving the talk today almost. My goals might be different from your goals. So as we judge the system, we end up with different expectations and different determinations as to whether the system is working well. There's a principle in autonomy of components, really individuality, which goes to microservices and to my own kind of promise theory, which is that when you have an independent component, an independent agent, it is the origin of its intent. So we bake into a particular component an intent, what it is supposed to do, and it sort of makes that promise. Like when you see a resistor or capacitor, it has something printed on the outside. I promise to resist 100 ohms plus or minus 5%, or I promise to hold 10 microfarads or something like this. That's a promise which is written on the outside of this component. That's what it intends to do. When we put it into a bigger context, its intent may not matter anymore. So as we scale up, intentions can often become washed out by scale, which is an important point. Now, 10 years ago, actually 2001, I think, I wrote this monolith for 2001, trying to understand how systems behave from the perspective of physics, again by observing systems, seeing what they did and trying to describe it. Not by asking how do we program them, or do they, are there better ways to program them, but simply by saying, let's just observe the animals in their natural habitat and see what the computer does at different times of day. And we made a bunch of measurements, and that led to a particular view of systems which impinged on things like queuing theory, resource consumption, again, system boundaries, planning constraints, variables, and a particular point of view. And this seemed kind of interesting, and it brought together a bunch of fields in computer science that hadn't really been closely connected. So it brought system administration close to things like queuing theory, which was popular in networking, but the networking people didn't really talk to the server people at that time. And so there were these very different worlds. So it was an attempt to bring all of those things together. But when I finished this, I discovered that there was something missing. And that was when you only look and see what systems do, what they actually do, you miss the key point, which is that when we build a system, it has a purpose. It has an intent. And so the intentional part of systems, why we build them, what they're for, the functional aspects, that was somehow missing in this picture, and so we needed to put that back in. That's when I came back to something called promise theory, where you try to discuss what promises does a system make and how can we track that. So, How does a system work? How do we know a system is working well? What does well mean? Well, again, everyone makes their own judgment, and it's when we find it meets our expectations. And we may form our expectations from what the system promises, or we may actually have no idea what the system promises. We may not have read the documentation. We may simply start to use the system and have some prior idea of what we think the system ought to do. And then we start to measure it and monitor it, and we start complaining to the ops guys and saying, look, it's not doing what I expect. And if the ops guys were smart, they would say, do you know how do you know what to expect? Have you read the manual? Have you read the documentation? Sometimes they do that, of course. So there is often a mismatch between what we expect and what was actually offered. I love this cartoon from a very old cartoon. We have met the enemy and he is us. Sometimes we are the enemy of the system because we don't have clear expectations. We don't have a reasonable set of expectations as to what a system should actually do. Rather, our expectations are based on assumptions. They're not based upon promises that have been made by the designers of the system or by the operators of the system. They're just guesswork on the part of the user. So the agent itself is the origin, the source of truth, if you like, about what a system is supposed to do. And that, I think, is an important point. That led me to this notion of promise theory, which added to that earlier book, if you like. I wrote a couple of books on this now, which really tries to address the subject of fitness for purpose. How do we know a system is fit for its purpose? Well, it makes a certain promise, and we should be able to check. We should be able to assess whether or not it kept its promise. But if it hasn't made a clear promise, how can we check? How can we know? We can't. We can just guess. So how do we know a system is working well? What does that mean? Well, do we mean, do I like it? Or do we mean, is it working well compared to what the manufacturer of the system, the author of the system, intended? What they promised? Is it keeping its promises? And this, I think, is a more important way, a powerful way of addressing whether or not a system is working well, that we need to think about when it comes to monitoring. And I'll come back to that in just a second. Excuse me. So fitness for purpose, desired outcome. We talk about this idea of desired end state. And I think one of the arguments that I've tried to make over the years is that systems should not simply make changes. We shouldn't think of deltas or diffs or commits as being the changes. We should think of convergence towards a desired goal, a desired end state. This notion of convergence I introduced in CF Engine for configuration management, where you, instead of typing a bunch of commands in a certain sequence or running a script, you define the state that you want to get into, and the system brings it always towards that state. And if it should wander out of that state, it can bring it back into that state. This notion of a desired end state is a promise. You can promise that the system will be in a certain state most of the time if you have a process which is designed to keep this promise over time. But if you haven't promised what it's going to do, if you've only said, well, we can do these commands, we can make these changes, how do you know what it's going to be? We have no idea what the outcome of all of these changes might be. Depends who did it, when they did it, in what order they did it. That's not good enough. If we want to be able to say specifically, is a system fit for purpose, will it do what we say, is it working well, then we need to be able to specify the desired outcome. So we think more in terms of outcomes and less in terms of changes. And this is an unusual thing. So if we go back to the question, how do we know a system is working well? We don't often ask ourselves that question. More often we ask ourselves, am I doing a good job? Because we think of ourselves. How can I make a difference? And what that results in is that when people collaborate in teams or work for a greater purpose, which is a systemic purpose, they don't always act in the interests of the system. They act in a selfish way, or selfish is not the right word, but a self-centric way. They think of themselves, am I doing a good job? And maybe their idea of what is a good job is different from the system's idea of what is a good job. So I think that's an important distinction, which promise theory tries to get a handle on by saying, how do we understand a system as being a collection of individual things that make promises to one another? So in promise theory, we define agents as people or machines or components. We define promises as the promises that they make to one another. And they come from within the agents, not from outside. They're not forced from outside. They're not obligations from outside, but they're promises from within. And we define an assessment as somebody else's evaluation as to whether this agent has kept its promise or not. And the basics of promise theory say that an agent can only make a promise about its own behavior, because it's the only one that has the power to change its own behavior. Other agents from outside may influence the total behavior of the system, but they can't change what happens inside the component. Obliging others from outside, trying to force people to do things, trying to give orders, type commands, remote control access, R shell, SSH. This is an ineffective strategy because you may not have permission. You can try to effect change remotely, but if you don't have local, close, immediate access, that may fail. The system may not cooperate. And an agent can only assess others' promises from its own perspective, because each agent sits in its own world with its own boundaries, its own constraints, and sees the world from a particular point of view with its own calibrated scales, its own reasons for making judgments in a particular way. And this includes both people and software components. Software components, of course, are just proxies for people. So they've been programmed to have certain expectations by people. And then reliance or dependency on other agents can easily invalidate a promise. So if I say I can promise you I can promise you a pizza at 7 p.m. last night at the meetup, that might be a lie, because I may have to depend on the ability for somebody to transport the pizza through the traffic. So I can say I could make a conditional promise. Yes, I promise to deliver the pizza if the traffic is good, or if the traffic promises to, do such and such. And unless I take account of those dependencies, I cannot claim to keep a promise. So this notion, we're almost taught in computer science to build dependencies into systems, break things up into modular parts, and connect them back together. This makes very fragile systems. So we're taught to build fragile systems in IT. And this is a problem because it means that we tend to make promises that we know, or should know, that we cannot keep. So we come to the problem of faults. Is the system working well? Is it working at all? Well, the history of faults is actually quite an interesting story, because this goes back to, actually it has a long history in Norway. It's a couple of famous statisticians from Norway, from the math department at the university here, developed the theory of system reliability. And the idea is that you look at components and you think that these components are mass manufactured, and there's a certain probability that a light bulb will fail at a certain time, and you can measure statistical properties, the likelihood that a light bulb will fail in a certain time. And then you can put them together into a big system and compute the effect that this may have on the total system. And this is a well-defined mathematical procedure. But it's based entirely on the idea that it's either working or it's not, from a component point of view. What it doesn't take into account is a modern software perspective where different components have different functions and the relationships they have between the different functions. You couldn't model, for instance, the idea that a certain person doesn't have permission to access another component. So the semantics of system design are missing from this classical picture of system reliability theory. So I wanted to try and put that back through this promise theory that I'm talking about in the project that I showed you at the beginning. And I tried to work on this and ask, what does this mean for us? Can we even define what we mean by errors, faults, failures, and so on? And there's a whole movement talking about the resilience of systems that likes to argue that actually we can't always talk about what it means to have an error. People often blame humans. It's a cheap trick, right? A plane crash or some major disaster, and so it was human error, which is kind of a cheap shot because it's always human error. I mean, you can always, if in any chain of causation, you can always trace back something to a person eventually. So you can always point a finger at somebody if you want to, but that may not be really the relevant thing that made the problem occur. So that's kind of a cheap shot, an easy cop-out. But if we can define the notion of errors and faults and failures more clearly, as I tried to do in this project, then we have a hope of being able to address the question more objectively, more reliably. And I made these definitions. I don't want to read them out to you, but you can look at them later on, or you can read about them in the document. And I think by making these clear definitions, we can make progress. But there's something, again going back to dependencies, there's something that all of these definitions rely on, and that is there are two aspects to systems. There are the semantics that I talked about, the purpose, the intent, what we mean for the system to do. And there is also the dynamics of the system. What is it capable of performing? Its performance boundaries, its capabilities within a system. Is it even capable of doing what we've asked of it? When we come to scaling, elastic scaling or manual scaling, which turns into queues, which turns into thrashing, which turns into all kinds of detrimental effects to system performance, these are dynamical effects. And the key lesson that I learned from the last 20 years, which I've been writing about, is that these dynamical effects limit everything that happens in the system. Everything is built on what the system can perform dynamically. If it can't perform, then it can't have the semantics we want, which represent our business proposition, our business purpose. So semantics always ride on top of dynamics. Dynamics come first. Can a system keep its promises and still be unpredictable? So can we have described a system to keep all of its promises and still not work? Sure. This is what happens when we connect things together in unknown ways. We can't always predict exactly how components, once put together, will behave. So this is a really important point. We can't simply design systems in UML or some nice planning language, some nice architectural language, and hope that the system will do exactly as we expect. It simply won't. The idea of knowledge itself, I think, I often say knowledge is the challenge of the next decade, but I've been saying that for a decade already, so maybe more than that. How do we even know what a system will do? Well, back in the beginning, I tried to ask this question by measuring systems. Back in the 90s, we just measured systems to see what they did. And we found that they often have very predictable and regular behaviors. This is just traffic from Samba, I think, Samba traffic, server traffic. And you'll see this, these peaks, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, not much going on. And this kind of trace has since been measured many times and reproduced by many people in many different places. It shows that our computer systems are driven by the most part, by what we do as users, our working week. This is our working week. And the peaks are around lunchtime, and the troughs are around the time when we're sleeping. This is a typical pattern. We can learn these patterns only by repeatedly visiting the system again and again and looking and knowing it like a friend. Remember this expression, to know the system like a friend. But this is what we usually do. We just throw up some sort of random variable like a CPU or bits per second on a simple time series graph, and we look at the current level right now. And we say, okay, we've got this sensory input. What does this mean? This has no relation whatsoever to the purpose of the system. You have no information in this picture telling you whether your system is working well. You simply have it's like taking your pulse and saying, am I doing a good job at giving this talk? These things are not really correlated very strongly. I mean, if it stops, we know there's going to be a problem. Well, it might not be a problem for you. That's a subjective, we've already established that's subjective. But this is the state of monitoring today. This is the state of the art of monitoring. It's rubbish. It's rubbish. What we can do, in fact, is what is now happening in artificial intelligence or cognitive computing, and this is actually, I worked on this back in 2000 for CF Engine. We had machine learning patterns of behavior over time, and then combining this long-term memory of learning patterns with what's happening right now, an immediate sort of assessment of what's happening right now, and using those two things together to make decisions about, do we need to adapt system behavior to take into account anomalies, irregularities in the behavior of the system. And this was tried. I won't say it had much success because I think it was too early for people to really think that this was a good idea. But now that we're really getting back into the swing of AI, I think this could well come back. There's this sort of knowledge ladder that we have for systems, again, trying to know the system like a friend. We start out fiddling around, trying to figure out how to do stuff, and then eventually, as we get better, we figure out what we can do to make a system. And then often it's only then that we figure out why we're trying to do it. We tend to start with putting stuff together, which is why we have these bad habits about not properly defining the promises that a system should make. Because we start out by trying to see what can we do? What can we even do? And until we can answer that, we can't say, what can we use it for? But if we continue to climb this ladder, there is a point at which we end up with goals, which can be promises, clear promises. I like to use this picture to illustrate the transition from experimenting to utility or commoditization, which sort of reflects what's happening in our data centers. When we think of agriculture, we start out, hunter-gatherers picking berries in the forest. They're pulling things off trees where they can find them. And this is hard work, so eventually we find tools and technologies to help us, and we can make tools to extend this manual process. But then once we've made the automation, we realize that actually making the automation work like a human would work is inefficient. Maybe there's a way to redesign the system to keep the same promise more efficiently without having to copy what a human would do with a body. And then we can depersonalize the whole thing when we know what we want to produce with this kind of hydroponics style, completely dehumanized environment, but it's much more efficient. By totally rethinking and taking the human actor out of the loop. This looks pretty much like a data center, and there's a good reason for that. It's because we try to take out the humans and use space and time to stack things efficiently. So how do we know our systems are working well? We have a bunch of questions we can ask now. Is the system keeping its promises? Is it going to fail because of scale or unexpected consequences? How can we begin to measure it? What kinds of things should we begin to measure? How can we learn if it's going to keep its expected behaviors? So I will leave you to the picture of the book that I mentioned at the beginning, which explains some of these points. And I hope that some of these points will give you food for thought for the rest of the day, and perhaps maybe even longer than that. So with that, I'll wish you a very good conference, and thank you very much.